Thank you for your introduction. First of all, I appreciate the invitation to come up here and talk. So I'll talk from very kind of user perspective. So I'm an assistant professor at North Carolina State. I'm actually nuclear engineering department. So I'm doing some high fidelity simulations, as you will see, on multi-phase, bubbly, turbulent flows using very expensive methods. So use a lot of HPC and need more of it. So, and I'll tell you some numbers what would be really interesting to have in coming years. So I'll briefly show what NC State is about, a couple of slides, and then I'll talk about the code which we are using. This is a research code which is used in a few universities, so it's not kind of very popular, but it's very efficient and it's very scalable, and you know it's quite amazing what that code can do. And then we'll go through some examples, and I'll look a little bit in the future what we're really interested in. So, well, College of Engineering. So we have about 9,000 students in the fall. We have 160 million research expenditures, and we're 10th largest undergraduate, 9th largest graduate, 8th number of bachelor's degrees awarded, 14th master's, and 16th PhD. So it's a pretty big college in North Carolina, and School of Engineering is in North Carolina is the best one. So our department is actually one of the oldest ones in nuclear engineering, and it was like physics department originally. We have the oldest nuclear reactor, research reactor operating in the United States. So, and we're actually growing pretty rapidly. So we have this nuclear renaissance going on. So our faculty numbers grow by a factor of 2 over the past 5 years, which is for small departments like ours is pretty amazing. So yeah, from 8 to 14. I'm not going to go through all of those. So, but just to start talking a little bit more research. I think this is the only equations, or almost the only equations I'll show. But bottom line, we solve, mass conservation, momentum conservation to solve the fluid, but we fully resolve the turbulence. So we have very little closure loss, very little uncertainty. So sometimes you can call it virtual experiments. But in order to achieve that, of course, you have to have a lot of mesh, and a lot of mesh is expensive. Hence, HPC again. So these are some examples which the code has been used. It's both multi-phase flow, so this is annular flow, so you have liquid film with droplets and bubbles in a pipe, and it has been validated against experimental data. This is some biological application, not in my group, but using the same code. So we have highly anisotropic meshes. So this is actually a blood vessel, and they did a very big mesh on a whole human body vessel system simulation, and quite challenging, but highly scalable. So this is something I've done 5 or so years ago, and this is basically a sort of accident scenario in a future design of nuclear reactor, and now you may understand why the simulations are important, because you don't want to design an experiment and design a nuclear accident and see if you can play with it. So you cannot really do it at all. So it's important to be able to model these kind of things at a physical level of fidelity. And this is one of the recent work. It's basically bubbly flow interaction with turbulence as a frame. And we did some 60 bubbles here, and I'll show you later a movie of that. So the reason I'm kind of sticking with this code is because I worked with it being a PhD student at Rensselaer 12 years ago. And it was developed in the 90s, and it was constantly upgraded, but was mostly used for single-phase simulations, and I'm bringing some multi-phase. So talking about scalability, it was some interesting tests done last year, I think, or beginning of this year, on Blue Gene mirror machine at Argonne National Lab. So 11 billion element mesh was tested up to 3 million parts on having up to 4 parts per core, so basically multi-threading. And the scaling was pretty amazing, going from 32K cores to all the way 768 cores. So you can see the efficiency drops down here by this factor. You have some actually super scaling, whatever it's being called in here, but then it's going maybe to 80% or something. There was some other tests done on Eugene in I think it's in Germany, Blue Gene machine at Kraken. It's some older results, and again the scaling factor going from 16K for this 5 billion mesh. This was 5 billion mesh was the problem which I mentioned about the human blood system vessels, the whole, everything in the human body. And it also went from 16K to all machine size with 80% efficiency. So one simpler example, so you understand kind of better the complex of the physics and why it's so much mesh is needed, which you'll see later on to represent it properly. So this is something we do actually, not even on HPC. I have a local cluster with 400 cores, and those runs maybe 64, 128 cores. So it's sort of almost laptop territory, almost there. And basically we place one bubble and we apply some forces to control this bubble, and it's in a shear flow with relative velocity. And this way we can measure by keeping the bubble steady what it's experienced. And this physics is very important to provide closure laws for the modeling approaches, which with much coarser meshes when you cannot resolve the bubbles, but you have to supply the models what kind of forces are acting on that bubble. And we did some validation so that our method works pretty well for the drag force against experimental data, and there is some explanation for that because the bubble deforms, and we experience a little bit more drag than analytical experimentally validated correlation provides. We did some studies, and this movie doesn't show properly somehow, but basically playing with the bubble, getting it to the wall, also measuring something here, and again providing the information for modeling. This is a little bit also interesting result when we still have a simple laminar flow, but we do resolve the bubble, and we do resolve some unsteadiness and sort of wakes due to turbulence or invoking turbulence around the bubble, and also kind of getting some results. Again, all those runs are about 1 million cells, 64 cores, 24 hours, so it's kind of barely HPC or way below that. Okay, and then of course we can do a bunch of simulations with different shear rates, and we can develop new correlations, which is difficult to be observed experimentally. And of course computations are nice, because for this you can do so-called separate effect studies by changing only one parameter versus in real experiments. Normally if you change the fluid by changing surface tension, a bunch of other things are changing, so it's difficult to isolate what is the effect of and difficult to develop new correlations. Now this is getting a little bit more interesting, so it's a little bit more expensive simulation, a little bit more challenging, so you're actually feeding single phase turbulence through boundary conditions, resolving those turbulent eddies acting on that bubble. Again, you're keeping it steady, also challenging, and the conditions are getting similar to what nuclear reactor cores are experiencing, but still we keep the Reynolds number pretty low because it's too expensive to fully resolve it, and we'll get to it in a moment. Okay, so this is another movie which basically I showed you a frame. Now we're getting to some sort of HPC. So it's 20 million mesh, and we run it, I think, at 4,000 cores, maybe on 10,000 sometimes. This was about 5 million CPU hours we used. This is only a portion of the simulation, so we actually ran it for about 30 flow throughs, what means like a single bubble would cross that domain 30 times, so we can collect enough statistics and actually obtain useful information from this virtual experiment. This is the same simulation, again, fully resolved turbulence, but just different view. We actually show those turbulent vorticities growing, and we investigated in the paper which we published last year how those bubbles affect the turbulence, and how one should modify the models on the coarser scale when you cannot afford to resolve them on the CFD scale. So we're looking at some more challenging simulations, and oops, oh no, nothing happened. It's actually replaying from the beginning with putting more bubbles, etc., etc. So another thing which we look hard, we do realize that HPC is expensive, and we do realize that our needs are beyond what you've seen. So and we really want to develop new tools, and that's where kind of data analytics comes in. But here it's highly specified, and we're kind of trying to do in situ analytics, if you wish. So one of the things which we been working with one of my grad students is coloring those bubbles, make sure we can distinguish them, and learning how to extract the information surrounding those individual bubbles. So once you run the simulation, not with 60, not with 100, but with 10,000 bubbles or 100,000, you can kind of have some pattern recognition and different statistics collected, so you can really provide a newer level of insight into that phenomena compared to expensive experiment one can run and measure basically the pressure drop in that bubbly flow, but have absolutely no idea what's going on with individual bubble, how they interact with the structures, how they interact with the turbulence, etc., etc. So we do have some kind of some basic results as well. So we can put virtual probes and collect the information as the flow goes through the subchannel. We get some turbulent fluctuations. We get some sensors, virtual sensors, which look at those bubbles, and then we can do some averaging, and this is kind of post-processing step. This kind of related to the data storage requirements, since once the mesh is growing, you cannot really afford to fully save all the steps. So we do save frames once in a while, but we can monitor continuously this limited number of nodes. So this is about maybe 5,000 or 8,000 points here, maybe less, compared to 20 million or 50 million mesh size. Okay, so talking about 50 million mesh size, so this is a different geometry which I kind of already introduced, but this is more related to nuclear engineering. So it's typical reactor subchannel. So you have actually nuclear fuel rods here, and the heat is being removed from them, and you have some boiling going on, and we want to model basically two-phase flow in that kind of geometry. And that's another reason why I was working with this code, because it's not only scalable, but it also can have unstructured meshes. And I'll show some more examples in a moment. So, this is just example of meshing tools, mesh results which we use. So the movie which is showing here is basically demonstrating how do we take and generate turbulence by placing a kind of an obstacle and providing those wakes, and then we actually slow it down with the current number, so we fully resolve the turbulence. So we don't want to waste time by waiting when laminar flow will become turbulent and burning 50 million mesh simulation at the same time. Okay, and then we place the bubbles and we simulate the bubbles. We have somewhat different requirements. So again, you're restricted by the time step pretty heavily when you want to claim that you properly resolve bubble deformation, bubble coalescence, bubble wall interaction, these kind of things. And again, you have, for this simulation, you have 17 bubbles, and this is the 50 million mesh. Okay, so if you can imagine a boiling process anywhere, it's more than 17 bubbles. It's hundreds and thousands and maybe even more. But according to this, approximately we need about 3 million points to resolve not just single bubble, but whatever fluid surrounding it. A certain fraction of bubbles. So, and if we collect something, we can get some statistics. We can compare with correlations. We can extract new values, and this can be used as a coarser model scale, CFD scale, boundary conditions, and other necessary closure laws. All right. So now we're playing, of course, with larger meshes. So this is 320 million mesh. 72 bubbles. This is really a trial run to make sure we can do it. So we got some hours recently, so we actually proceed and perform that. But one of the approaches also we need to debug our tools in this advanced analysis. Okay, so this is in our simulation. This is no bubbles here. It's a quite low Reynolds number, but the mesh is quite complex. So this is a 2x2 reactor subchannel with mixing vanes and spacer grids. So what it is basically support structure for those fuel rods in the nuclear reactor. They also play a role of better mixing the flow, avoiding some dry spots during the normal nuclear reactor operation. And we can do it, which is nice. Another thing which I wanted to mention, there was some discussion on in situ yesterday, I think, and we had some effort done actually with our code, so those images were generated in form of JPEG images as the code were running. So we didn't even actually save the whole data set every time step or every 5 time steps to produce this movie. We just made the images and we saved the data only every 1,000 time steps. Now, but this is very, very low Reynolds number compared to what reactor experienced. And unfortunately, when you do direct numerical simulation, your mesh requirements are going up as a factor Reynolds to the power of 2.25. So if you have to increase it by a factor of, well, it's about 120 from where we need to be. So you have to take 20 and raise it to the power of 2.25. And then there is a time step restriction, so its overall cost is Reynolds to the power of 3. All right. So besides just running the bubbles and asking for more mesh and for more HPC, we also want to of course do more interesting research and go into more interesting flow regimes. So this is a so-called boiling water reactors, and you have not only bubbly flow, but you generate a lot of vapor as the fluid heats up. And so this last regime, which is shown here, it's actually droplets inside a vapor core and thin liquid film. And there are a lot of safety considerations why this has to be predicted. So thankfully, there is a nuclear renaissance still going on, at least here, and there are some newer designs which are being developed, and actually some of them being licensed. I actually got email yesterday that GE, Hitachi, EASE, BWR has been licensed by NRC, so we're actually moving forward with that small modular reactors. So things are looking up in nuclear. So I feel we're in a good place, and this type of methods can hopefully help bring a new generation of analysis tools, which typically were and still are in the industry, 40-year-old tools. So Castle, DOE Castle, and was presentation by John Turner, also helps a lot, and I'm working with them as well to bring new tools to nuclear. Okay, now what I want to show, and that's the future part in my title of the talk, what we can do now, what we can do maybe next year, and this is kind of simulations, and what does it require in terms of the HPC capabilities if we really want to do it. Other question, well, if we don't have it, then, well, we don't have it, we'll come up with something else, but what would be nice to have? Now, the mesh I showed you was 190 million elements, and it was 3.6% actually of typical normal operating conditions in terms of the Reynolds number, and I mentioned that those requirements. We can do something bigger, somewhat at the Reynolds of 500, and by the way, this Reynolds number is based on friction velocity, so it's for those who know what it is. This simulation would resolve about 600 bubbles, and so not necessarily this one, but close to that, and could be run pretty efficiently on 512 Mira machine where we have the allocation 500K cores, and the code which we use actually scales pretty well down to 3, even 2,500 elements per core, which is quite impressive. So and we can do that, but we're still kind of far away from what the real conditions in PWR stands for pressurized water reactors, which is 2/3 of the reactors in the United States. And this includes our 2x2 subchannel. What it means is that we're basically only considering the flow in between 9 fuel rods. So looking down the line, exascale comes along, and hopefully, maybe we can try to be bold and say we can do the realistic conditions, but still for the limited geometry. That's kind of my estimate for the mesh size, 350 billion elements. So it gets interesting. If we want to still run 4 elements per core, maybe having 90 million cores. I mean, I'm not talking GPUs here, so I don't know. I mean, what kind of technology we will have, but let's say I have the same blue gene, it's just huge, right? I mean, I'm simple. And that would resolve 120,000 bubbles. So that's kind of statistical point of view. It's very, very useful. Your realistic conditions, you can really do a lot with that already. Now, if we get greedy, what we can do, we can look at the fuel assembly. So fuel assembly is manufactured, and they have 17 by 17 fuel rods, and that's actually how those spacer grids look like. And of course, they interact with each other. So if one fuel rod is heated more than the other one, I mean, the flow is different. I mean, it's kind of an important point. And this suddenly, and by the way, it's not 40 centimeters long. That's what we use. It's 4 meters long. That's kind of the whole reactor core height. So that would be already 256 trillion elements. So that's a good number. I mean, I use just my calculator and I come up with a bunch of numbers. But this is something would be really interesting to do. And well, now I'm saying, okay, I'm okay with 16K elements per core, but I'll still need 16 billion cores. So this is extremely interesting. So I don't know. I put 2030 there, but who knows? It could be 2300, right? In terms of capabilities. And if we get very greedy, and I don't think there is too much reason for this, but I'm just saying that there are problems out there if you want to apply DNS to, which will require some extreme computing. So the reactor core consists of 160 of those assemblies. And of course, those assemblies are different. So really want to claim you want to do DNS, resolving every single bubble in a 3,000 megawatt thermal nuclear reactor using HPC, then you would need, what is it? So I don't even know what it is, but it's 40,000 trillion elements. And we could use 320 billion cores, and we'll have 13 billion bubbles. So, very interesting. There are time domain issues, and of course, computing cost we have to justify. I mean, if it's free, then yeah, we can do it. But if it's cheaper to build a brand new reactor than to run this simulation, then of course it doesn't make sense, right? This is my conclusion. I'm not going to read it through since my time is run out, but I'll be happy to answer any questions. Thank you.